So we are looking at the concept of reversible work. Say we consider a piston and cylinder arrangement of which pressure is acting on the walls of the cylinder, on the boundaries. Now, and we have a fluid inside this cylinder. So if we calculate the work done by the fluid, we can write that the pressure times the area, which represents the force, times the differential length, the L, gives us this equation of that we call P dV. That is where dV represents a small increase or a differential increase in small increase in volume. Or if we write it for a unit mass, we write this setup for a unit mass. For a unit mass, we can write work done is equal to P times dV, where V represents the specific volume. Okay, represents the specific volume. Okay, but this formulation only depends on, it only holds true when we have the following assumption in place, and these are the assumptions for this. So when a fluid undergoes a reversible process, the series of state points can be joined by a straight line. So if we write the PV diagram, if we draw the PV diagram of this process, say we have state point 1 through its various states to point 2, and it follows this path where we take a differential path dV. This is PV diagram. And then we take the area under the curve of the PV diagram. We take the area under the curve of the PV diagram. We will get this concept of work, which we write as work done for this setup. The PV diagram gives us integral from 1 to 2 P dV. Now, if we want to get the work done in this integral, we would need to have P in terms of V. So when we have P in terms of V, we can then evaluate this integral. The next concept we want to think about is the concept of internal energy. So the internal energy represents the heat stored in a gas. So when heat is supplied to this gas, one of three things or all of three things may happen. Temperature of the gas increases, or volume increases, or both increases. So this will lead to doing some external work And whichever of this process of these things would happen depends on the condition of heat addition. Now, if during the heating of a gas the temperature increases, the internal energy of that gas will also increase. So if during the heating of a gas, when we have this and we supply heat, Q, remember Q is entering into the system. We said heat supplied to the system is positive heat, while heat rejected is negative heat. Okay, so we have Q entering into the system. The temperature of this system will increase. Temperature increases, which implies that the internal energy will also increase. This concept can be thought about when we discuss the Joule's law of internal energy. So, Joule has a law that states that internal energy of a perfect gas, the internal energy of a perfect gas is a function of temperature only. So we can write U of a perfect gas is equal to a function of T only. So we can then state from this law that the internal energy of a gas doesn't really depend on P, pressure or volume. It depends on T, mainly on the temperature of the gas. And this concept comes from Joule's law of internal energy. So, in engineering, we do not know exactly what each state of U would be. We do not know how to find the absolute quantity of internal energy in any substance. What is needed, however, is the difference in this quantity, which we present as delta U. So this takes us into the concept and the law of conservation of energy.